Laser pointer.
Okay, hello everyone. I think by now, at least some few. Yes. Oh. Yes. Yeah, there's some here. Oh, yeah.
I don't know about this. Then maybe that will go away. It will eventually go away.
Hi everyone. Unfortunately, it's not me presenting today, so I'm just gonna introduce the speaker for today, which is Jureya, who is currently our PhD student in the geoscience in hydrogeophysics. Jureya is a BSc and honors in geology, which she completed, and then she started her MSc with us, and then now she's doing PhD, as I've mentioned. And her current research interests include near surface geophysics, hydrogeology, and UAV aeromagnetics for water management, sustainability, and mineral exploration. She is currently our president, as we always refer her as. She's the president of the Wits EAGE Society student chapter, and she's also the award recipient for the lightning talk for her research at the 17th Saga conference that happened last year. So I'll just give it to you, Jureya.
So today I'm going to be presenting my research, which is the groundwater circulation in the shallow crystalline aquifer of Jureya mine, using environmental isotopes and near-surface geophysics. So we recently published this data in a paper that's now available online. So please go and have a read. But this paper was published in conjunction with two other papers, one by our Sikelela Gomo, which is the integrated geophysical methods for boulder delineation, and then our very own Kenneth Rapetswa, who now has a paper in review trying to map some structures and fractures. So just the overview, image on the left is just the problem that we're facing at Teresa Mine. So as you can see, there's a high flow rate, which is kind of unmanageable for the mine. So we were trying to help solve that problem. So the problem that we have with mining and water involved with mining is that we have various environmental impacts. So we have acid mine drainage, heavy metal contamination, sediments and erosion, process chemicals that can be leached into our from our tailings into our groundwaters. So we're trying to find ways to mitigate these risks. So there are companies that are doing various work, trying to manage this groundwater flows and everything. So we're trying to minimize these environmental impacts. What we had is that we had our open pits, which was being dewatered, but now filling in from various sources. And the problem is we didn't know where these sources were. So now there's so many different sources that could have been caused. And now we're trying to say, what is the actual source? Where is it coming from? Is it a seepage? Is it just infiltration into our aquifer? Is it via fractures? Now that's what we're trying to do. So this research is important because we need to find a way for mining and the future of mining so that we can use this water in a more sustainable way and mitigate those risks that are associated with it. So now that's why we were able to do this project. So to find all those causes, we had to conduct hydrogeochemical and geophysical investigations to assess our groundwater quality and find the water sources. To do this, we use stable isotopes, which are our 18O and 2H, and also radioactive isotopes, which are our 3H or tritium. And then we also use various geophysical methods, including resistivity, surface wave analysis, magnetic and seismic surveys. So just the study area, the Teresa Mine is located on our southwestern limb of our Bushveld Igneous Complex, and it's classified by our Rustenburg layered suite. Moreover, what we are focusing on in the Rustenburg layered suite is our critical zone geology. So this is characterized by our anorthosites, anorthites, pyroxenites, hosbergites, danites. So with our methods, we sampled various places in the pit. So if you look at this diagram, the red dots are our surface water samples, and then the white stars are our borehole samples. We sampled various areas in the pit. So we had our far west pit, our west pit, our east pit, and then our 2 tailings dams. So we had tailings dam 1 and 2. Along these tailings dams, we also are now going to focus on our seismic methods. So in tailings dam 1 and 2, we did resistivity and MASW, which is our surface wave studies. And then in the east pit, we wanted to associate our studies with known geological structures in the area. So we have our dike that we knew was passing through the pits. So we conducted these blue grids, which are our magnetic surveyed areas, trying to see, can we associate any of the lineaments to the water that we were sampling. So with our hydrogeological methods, the way we went about this is that we sampled our isotopes in the pits, and then we analyzed it here at Wits using our liquid water isotope analyzer. And then with the tritium samples, we sampled them in the pits, but then we had to submit them to a timber lab because we don't have the equipment necessary to do the analysis. So again, this is just the problem that we are facing, this water that was seeping into the pits. With our stable isotopes, we plotted it against our total dissolved solids, which is our TDS. And what we noticed is that there was a correlation between our total dissolved solids and our isotopes. We noticed that the more enriched our isotopes were, the heavier or the more TDS they had in the samples, meaning that they were more polluted or contained heavier isotope values. When we plotted the 2 stable isotopes against each other, so our delta 18O and 2H, here we were trying to see where are sources for the water. So we plotted it against our known meteoric water lines, and what we had was various sources. So we had our very depleted isotope signature. So when you say depleted, it's your groundwater that's been circling for over 1,000 or millions of years, right? These are the waters that are in your deeper aquifer. Then what we also had was more enriched, or isotopes with a higher concentration. So these are isotopes that are being exposed to fractionation. So what happens during evaporation is that your heavier isotopes are left behind and your lighter isotopes get evaporated. That means that, okay, now you're going to have a more enriched surface water signature. But we also had this zone here, which displayed a mixing signature between depleted and heavy isotopes. So the possible reason for mixing could be along lineaments, could be infiltrating down different surfaces and things like that. So it didn't really help us identify possible sources, but it kind of put us on the right track. So then we were like, okay, can we associate what we know with our electrical conductivity? So when you have electrical conductivity, it tells you your degree of mineralization in your water. So if it's more salinated, you'll have a higher electrical conductivity because obviously it's going to be more enriched in your oxygen or your 18O. Now, again, during evaporation, the same process is going to happen. You're going to have heavier isotopes being left behind, enriching your surface waters. Low electrical conductivity values may be associated with more recent recharging waters. So this could be recent rainfall or things like that. However, the problem is that high EC can also be associated with increased water rock interaction. So when your waters go or descend along lineaments, they react with the composition of the rocks around it, and it increases their isotope signature. So what we had here when we plotted our EC against our 18O is that we actually had a negative correlation, meaning that our 18O and our conductivity did not have a linear relationship in such that we had more samples increasing electrical conductivity without there being many changes to the delta 18O. So that means that it could be that there was some water that was enriched with heavier isotopes and then being increased in our EC, suggesting maybe recent recharge with evaporated waters or mixing with the unsaturated waters or river water. So this begged the question is that, could it be that repumping was the cause of the water that we were seeing in the pit? Because when water is being pumped via lineaments and used for dewatering, it can re-enter the pit via lineaments or by the river, right? So what we saw in the pit is that we actually had a fault dike intersection zone. So we have our dike over here, and then we had a fault zone. And when we saw where the 2 points intersected, it had a very unusually high flow rate, about maybe 1 liter per minute. So now that could also be then, does that mean that lineaments are now increasing our permeability and our porosity in our rocks? So now we use analysis. So what happened with the tritium analysis is that, remember, this is your radioactive isotope. So you can use this to actually date your surface waters by radioactive decay, because tritium has a half-life of 12.4 almost about 55 years, and then very young surface water, almost about 5 years. So now there was this deeper aquifer water mixing with now more recent recharging aquifer water. So when we plotted our tritium against our stable isotopes, we were able to see this trend. We had very deep circulating water that's been circulating thousands, millions of years, and then more recent recharge. So water with a higher tritium value. But we also had water that had a signature of 18O that was highly elevated, but a tritium signal that was low. So that could suggest that this was recent recharge from a depleted moisture source or from a geographically isolated area of influence. But now we also had a mixing zone, which means that we had mixing between our recent recharging waters and our deeper aquifer water resources. So again, multiple sources in this one mine. We tried to plot the tritium data in terms of a contour map. And what the contour map showed is that certain areas of different age, different tritium value had the same recharging year. Now, what could that be a cause to? We weren't sure. So then we tried to blow this image up and plot it in 3D. And what we noticed is that our higher isotope signatures, our more enriched signatures, were concentrated on our higher elevations. We had depleted isotopes on our lower elevations, and then along lineaments, we had mixing signatures. So that means that possibly along fracture zones or systems, we have this, again, this recharging water mixing with deeper aquifer systems, which again made it hard to suggest like what was the possible sources or cause of the water. Now, moving on to our electrical or our geophysical methods, the first thing we did was electrical resistivity. So we conducted various surveys, different spread lengths between 80 and 300 meters, and electrode spacings of 1 to 3 meters. And we used a multi-electrode unit to do this. The data was then collected, we despiked it, and then inverted it in Res2D to obtain 2D inverse models using our least square regressions. So this was our recording station, this is our resistivity meter, and this is our electrode. The next thing we did was the multi-surface analysis of surface waves. So we used a standard roll-along technique to do this, and we then processed the data on surf size. Note that safety is an important thing in the field. The data was then processed on surf size, and then a 2D model was produced from all our 1D CMP inversion models. So the sources we used, we had an aluminum plate to improve the coupling because it was a hard rock environment. And then we used a hammer as our source, and our receivers were used a land streamer. Just to note that this is the environment that we were doing the surveys in. So it wasn't the easiest survey, but we persevered and the results were worth it. So then the next thing we did was the seismic method. So with the seismic method, again, we did various lengths of 46 to 96 meters. Our shot receiving spacings were between 1 to 2 meters. And then we used 14 hertz geophones. We also used a land streamer and an accelerated weight drop and a sledgehammer as our seismic sources. In terms of processing, what was first done was fixing the geometry and then getting the CDP or the common depth points. Then the first breaks were picked, and then we applied our refraction statics to generate our P-wave velocity models. So this is our weight drop, accelerated weight drop. This is our seismic hammer. These were our receivers, so these are our geophones, and this was the recording station. In terms of the magnetic method, we used a walk mag. So we had our base station as our G856 proton precession magnetometers, and then we had our cesium vapor magnetometer as our rover to collect the data. What we did to process was to despite the data for the diurnal curve, then we applied diurnal variations, despite that, and then interpolated using the minimum curvature technique. So now our results for the geophysics sections. Along tailings dam 1, so our tailings dams for storage facility 1, when we conducted our resistivity and MASW results, we were able to see that there was this very high resistive feature, but then the zones of lower resistivity is about 24 ohms per meters. And then when we correlated it to the MASW that was collected along the line, we have zones of low size surface wave velocities. And what we know about low surface wave velocities is that we want areas with our higher seismic attenuation so that we know that those are our conductive zones. And we were able to see that there is, again, backing up our hydrogeology results, is that there's mixing between our surface waters and our deeper waters, possibly from these lineaments. For our tailings dam storage facility 2, again, we conducted MASW and resistivity studies. And again, we have resistive features. But then when we associated with the MASW along those lines, we again had these low surface wave velocity zones correlating to low resistivity zones, which are more conductive zones. So again, we have maybe mixing between our surface and deeper waters. It's important to note that even though you struggle, you still smile through it. We managed. And then our magnetic grids. So With our magnetic grids, we plotted our TMI models. So with the TMI, you have these very high magnetic areas and then magnetic low areas. Now, the magnetic low areas, we can see that it's fractured, or it's there's breaks or disjointed features along them. So we could say that those are possible fracture zones. And then the more magnetic zones, we associated with our dike that was moving across our study area. In terms of our fracture networks, we were able to correlate along various profiles our seismic and our resistive zones. And again, we see that we have very highly fractured rock and then more non-fractured or fresh bedrock. When we correlate it with the seismics, you again can see possible fracture systems. So here's our dike, and this is where we conducted the survey. So again, you can see that there's this fracture or fracture zone that is running in our diagrams. And then when we correlated it with the mag, the fracture zones were actually plotting on the areas of low magnetic intensity, meaning that we know that they were possible fracture zones. Then again, with the fracture networks, we can see that we had very low magnetic areas and highly fractured bedrock being associated with our areas of low seismic velocity, so our fractured areas. Then in summary of our results, what we did is that we showed that there was hydrogeological and geophysical techniques that can be used to identify our groundwater extraction zones and delineate various lineaments that can be used possibly to see what the connection between our upper and lower aquifer are. And what we found was that majority of our groundwater influxes came from different fracture systems or zones. And then when mine development occurs, there's a bigger aquifer volume that's being accessed, obviously due to the mining and digging into the pits. And then what happens is that this increases the aquifer's ability to transfer and retain water because it's increasing your porosity, permeability of your aquifer by fracturing it. The geophysical results, we did say, substantiate the hydrological results in that the main sources that we could conclude from this project was that it was the river water being recycled via lineaments, possibly when dewatering occurs, tailings dam seepages, and then obviously our mixing between our surface water and deeper water sources. So again, just so you can see, we have an area where we had a dike and a fault intersecting. And at this point, what we had increased flow rates and more seepages. So we would expect that there would be an increase in permeability and porosity in our rocks there. Now, our current work, just to summarize, we had papers that I mentioned. So here was the boulder site, and here was the fracture zones. And what we did now is that we conducted more ground seismic surveys. So why we conducted this is that we have a river that is flowing through here. And we wanted to see, is there any association between the river and fracture systems around the mine? And could that be a zone where we have a migration of water into the pits? And is there any association between those migration zones and the pits? So what we noticed is that we had different factors that were inhibiting us. For example, when we conducted the lines along the river, it was very difficult to cross the river. So we had to offset our lines quite a bit. And then we also had these boulders, which we had to maneuver and move around. We also had other sources that we will soon discuss. So what we did here is we used our Bobcat as our seismic source, again with our accelerated weight drop. And we had our geophones and our ROWs as our receivers. And then we conducted the survey along those lines in the pit. So just the summary of the data, you can see that this is our preliminary data. So this is line 1, 2, 3, 4, 5, 6. The data is still being processed. So this is just what we have so far. So these are, you can see there's a very clear refractions and reflections. So yes, processing those to see what are the associations between that. We also have sources of noise, as you can see in some of the figures. So the causes for this noise, so now we know that we had one line that was in the pit, which is this data. Then we had one line that was closer to community, which was this data. And when we compared the two data, or the brute stacks, we saw that this data was less noisy than this data, and we could see a very clear reflection in this data, whereas this data, it was very unclear as to where the major reflections were. So what were those sources of the noises? It was our drill rig, so our loading shovels, hauling trucks, any anthropogenic noise that we have in our mining environments. Then now the interesting part is that what we're currently doing is our UAV survey. So the first thing we did is we used our LiDAR survey. So this was flown at 100 meters flight length across the entire mine, and it was completed on the 29th. And then what we used this data for was to create an elevation model that would be used for our magnetic survey. So this is just a summary of the aeromagnetic data and equipment. So we had our drone, here's our magnetometer, and this was the setup inside the car. So then what happens is that the magnetometer lies at a depth of about 3 meters below the actual drone. And depending on your flight length, above ground is how high resolution your data is going to come. So in terms of the data, we had preliminary or previous aerial magnetic data. So as you can see from this data, what we were able to see is that there was a shear zone, there was a higher magnetic feature associated with the dike. And then we also had our different chromatite layers, so MG1 and MG2 and UG1 layers. And then we had a fault that was running through the area. Our mine or our study areas here. So this is a regional aeromagnetic study. So as you can see, the data are quite not clear. It's not that great quality, but the reason why we did our UAV study is that we could see that the quality or the features were more enhanced with our higher resolution data. So these two images are our LiDAR studies. So the blue areas or the white areas are our deeper elevations. So remember, the LiDAR again is used to create your elevation model. And then the green areas were our higher elevated areas. We then used our UAV to create our aeromagnetic data. So this is our TMI map. What our TMI map was able to do was see areas of higher magnetic intensity compared to areas of lower magnetic intensity. The features were not that enhanced. So what we did is applied a first vertical derivative filter to our data, and we can see that the features are more enhanced. So you can see now that there's clearly distinct lineaments as compared to our previous data, where it's not too clear of where the lineaments associated with the actual mine are. So what was good about this data is that it provided our detailed imaging of our geological features and structures, and then any artifacts or even boulders, dikes, faults, erupts. And this is also critical for planning your mine, because you want to plan a mine where you have many fractures, faults, etc. It also, and thank you. Yes.
Great job, thank you. On the first part, were you able to get any of the water? I mean, frequently the mines drill quite deep, and you were, if I remember correctly, your geophysics went down to 10, 15 meters. It wasn't that deep. So were you able to correlate that with any of the borehole influxes of water that you might see?
So we didn't actually have borehole influx values for the actual bottom of our open pit where the water was seeping into. So we did get, I think it had estimated values. I can't remember the exact numbers, but I can give it to you afterwards. But they were just estimates of the water that was seeping into the pit. We didn't actually have boreholes that were correlating to where we had the problems in the mine. So it wasn't really ideal to merge it with the geophysical data. Thank you. Well, we actually have a mine representative in the audience, and maybe he can answer your question. But I think they have improved their dewatering systems. I know they're pumping at a higher volume than they were initially, but I don't know if anything else. Maybe you can. Yeah.
No, there's no clear solution.
So it's
Still a bit of a challenge. And I think it goes to the question of what that feels, water coming from the southern side of the planet, where the dam. So we able to create any structure that are maybe responsible for water. At this stage, we have any structure that are thinking about.
So that's actually why we wanted to conduct our aeromagnetic studies, as well as do these new surface seismic studies, because it's hard to do a regional study of the lineaments between different pits, because remember you're limited by how you can move in the mines. Remember, you can't move everywhere in the mine to set up a survey. So finding areas where you can actually set up a survey is a difficulty. And then again, you're also inhibited outside the mine by your community, right? So you can't extend beyond that. So that was the point of creating this aeromagnetic survey, because it can cover a higher volume of land in obviously a faster amount of time, and then show you those correlations between different structures and lineaments. So that's currently what we're trying to do. So I did do physiochemical studies, and the water was very saline, obviously because it is reacting with the mining activities in the area. So again, not only just with the rocks in the area, but also mining processes and machinery, everything that's moving on top or on surface of the mine. And what happens is, again, the environmental problems that we have is leaching of these chemicals into the water. So, but now the volumes of water we have on the open pits is quite high, and to now get that purified would cost a lot of money for the mine. So it should be a thing to look into the future, is how can we sustainably use this water in different processes, like maybe taking the dewatered area, instead of repumping it, maybe take it to a processing plant and use it in the processing plant. But that again, it costs a lot of money. So mines, I don't know, are very limited in what they want to do. So they have quarries and areas. I think I can actually show you. So here are our pits, right? And then what we have, it's hard to see, but we have on top of or I don't know if you can see here in this image, there is dams that they are storing the water in. So this water is stagnant. It's not being used, I don't think, for anything. But I know when it comes to, so with the mines, a big problem is dust. And I think the dewatering water is being used on these trucks that are now spraying the roads to minimize the dust. But again, remember, that water is still going to seep into the pit, right, eventually. So it's not really a sustainable solution for the future, but they are doing that. Yeah. The problem of the water seeping back into the pits. Unfortunately not. That's why we have to see where are these structures and the lineaments. So I'm not sure exactly what they can use the water for, but I don't think there is any limestone. Tony, you can correct me. I don't think there's any plans to be using limestone storages and filtration to, again, purify the water. Yeah.
There is some work on planning to remediation, so using plants, but I don't know if you'll get deep enough
Yeah.
to pull it out beforehand, but it is a very big study area. But I wanted to say, the aromatic day looks very interesting, the new aromatic, I'm assuming you're still working on.
Yes.
And have you found any new fractures and dikes that you weren't aware of at the start of the study with the new aromatic?
Definitely a lot of fractures that are associated between the pits. The actual pits, again, remember, you're still going to have better resolution with the ground survey, the ground geophysical surveys, but we do have more fracture networks that are correlating the pits itself as well as outside the mine. So that's also why we wanted to conduct our MASW, our seismic surveys, again, to see if we can correlate those higher resolution fractures with our regional aeromagnetic studies.
So what is not shown here is that so one original and the one with the conditions what we have shown. But that period of keeping the mind, so actually we find so if you notice it's structural, but essentially those bodies and they're even so the new bodies, it's quite huge. So basically, and one of the issues of course was to it's in the peak, so of course it can see that coming from the Panama is coming from different parts. So it took a lot of time to actually getting the first part of the situation. In addition to the fact that a couple of times for a lot of times, so there's quite a lot of them coming. So they get an average in so many.
Any of the other obstacles?
The plan was
Accelerated weight drop.
Yeah.
It associates more with the penetration depth as to which your seismic waves can propagate. So the hammer, you're only going to get more of your near surface, whereas the weight drop can go to depths of Kenneth, I don't know, about 3 kilometers. Yeah.
Also, you need to remember that the study was divided into different phases, right? So the initial phase when we conducted the survey, it's when we didn't have the weight drop, right? So that's when, and also the weight drop logistically it's very challenging to use such a source in an active mine environment, right? While a hammer you can just walk with a hammer compared to that. So those are some of the things that you need to consider. That so on this last phase where Jureya was actually getting the survey, that's when we had the accelerated weight drop and everything. But on the initial phase, we only had the
the main thing was sort of when not
Is there any more questions? Okay, thank you. Can I stop there?
They were telling me that maybe we have.
Yeah, I think so. That was brilliant.